In this part, we will learn how to prepare optimum gels. So we learn our previous knowledge on optimization and factorial design and how to choose the right variables to get the best gel. The first question is, what is a gel? So as you can see here in this animation, we have a polymer, so large molecule, and that is hydrated. So basically we start with process of polymer dispersion, and then this is followed by the swelling of the polymer, because that will attract so much water molecules and increase in size. And at the final stage, if this is a medicated gel, then you will end up with adding the drug into it to allow the drug to be loaded. You will notice here in this animation there is enhancement in the viscosity, and that what gives the gel its structure and this strength, because if this network which is formed with the water molecules. So a gel is a thick, clear, semi-solid formulation or dosage form, and as it says, is made up of this 3D polymer network. It feels cool and non-greasy on the skin, and that gives a strong application, especially in wound healing or in the treatment of burns. So it has the capacity, or it can help with increasing the absorption. Hence, it's used in the Voltarol gel. This is a non-steroidal anti-inflammatory diclofenac, and aloe vera gel for burns, and hand sanitizers to help with the different hydration of the skin and incorporation of highly water soluble components. There could be different types of gels. These are shown here in the animation are the three common types. The hydrogel is where the continuous phase is water-based. Organogel is the type where the continuous phase is oil. And where you have the emulgel, you have a combination of water in oil, or a cream, or oil in water, or water in oil, or oil in water combined with the gel. So the application will be different. Often when there's a water soluble, then it could be things which are hydrogel. Sometimes what happens here, there is a drug which is more requires more oil in nature because it's more lipophilic. Then you could go for the organogel. Emulgel is also quite useful when there is a combination of properties, so it can be used for both kind of products. Emulgel is things like the ibuprofen gel, so that is topical anti-inflammatory. The organogel can be used for things like testosterone gel. So this is because testosterone has a higher oil solubility, and emulgel is the opposite because it can have oil and water, and the gel structure can help with the will help with things like as mentioned, ibuprofen, diclofenac, all these things. Hydrogel can be used as hydrating and also to relieve some pain, or could be things like burns or any irritation because it's more water rich. So this is the classical way to represent the gels or the polymer network. So as you can see here in this animation, the polymer longer longer chains, they can form hydrogen bonds, and they can form intermolecular hydrogen bonding. Those polymers are often here. These are examples. Common gelling agents like carbomer, cellulose base, and carbopol are classical ones that are used. In many cases, more of the polymer, that means it can lead to thicker gel. This is another way to imagine what happens here. So you have the dry powder, and then it is exposed to the water molecules. The water molecules, they penetrate through the chains of the polymer, and then eventually that will lead to swelling of the polymer chain, and that will lead to expansion of the network. One of the common kinds of thickening agents is carbomer. So it's a carbomer gel system. It's an acidic polymer, and that means it will swell when the pH is raised. So if it's you really need to generate some charges on the surface, and the way you do this is by changing the pH. So you're moving from a lower pH because it's an acidic, and then at one point that pH will lead to this generation of the charges which are needed to form the crosslinks and interactions. And the final pH should be around 5.5 to 7, because you don't want to end up with a higher pH, and that could be dangerous, of course, for the skin. In some kinds of polymers, we can witness something called sol-gel transition, and this is common in some non-ionic surfactants such as polyoximers. What happens here at a low temperature, there is enough hydrogen bonding between the polymer chain and the water molecules. When the temperature is increased, the water molecule start to move faster, and that might weaken the hydrogen bonding, and that means leads to aggregation of the lipophilic parts of the carbon chains within the surfactant molecule, and that leads to a compact structure forming to gel formation. There is often a temperature where this happens, and this is as is shown in this diagram. There is, at that temperature, you end up with the gel solid-like structure. So this is the sol-gel transition. The process of forming gels requires some steps to be followed, uh, but then these needs to be followed with some caution to make sure you end up with the right consistency of the gel. The first thing you do is to disperse the carbomer polymer in water. You need to sprinkle it slowly, because otherwise you may end up with lumps. And then you need to make sure you let it to hydrate. So leave it to swell for around 15 to 30 minutes. After that, you dissolve your drug in a solvent system, and often here we use ethanol-rich system, which is this industrial methylated solvent with propylene glycol. That will be used to dissolve the drug separately. And then the following step is to combine the two solutions. So you'll have the polymer solution or suspension, and you add it to the, or combine it with the other solution which contains the drug with the inside the co-solvent. At the end, once you do this step and you combine them, you add a neutralizer. And we mentioned we do this to raise the pH, because that will allow the cross-linking to happen, because that will change the charge at the surface. And we use triethylamine, and that will help forming the gel. That brings us to um, this design, which we have been discussing in other topics here, of factorial design and optimization. So we've got the first thing we do, we can choose the variables, and in this case we'll use the thickening agent, or the polymer, which is the carbomer. The amount of the carbomer that we're going to use or vary, and in this case it will be between 0.5, 1 and 1.5. We'll also use the solvent system, which is the IMS, or industrial methylated solvent, which is the alcohol system. This is the solvent, and we'll also vary this from 10, 20, 30. And I repeat that when you do the design, you should always use similar intervals. So you shouldn't, for example, use 10, 15, 30. It needs to have the same interval, 10, 20, 30. You would expect that more carbomer, that will be give you a thicker gel. More of the solvent will probably give you a thinner one. So on the other hand, thinner might end up with a better penetration. So you need to have eventually a better balance. It's important to understand the role of each component into the gel system. The carbomer is the polymer, and that is thicken. It will thicken and hold the gel together and keeps the structure that we desire. The IMS, or the solvent system, is the solvent which you're going to dissolve the drug, which is in this case the model drug we're going to use is the ibuprofen. It will help with enhancing the skin penetration. Propylene glycol is another solvent system, and it will help keep the gel moist and prevent drying. The base system, triethanolamine, that will neutralize the pH because carbomer is acidic, and that help with providing a charge, help with the forming a network. And of course, water is the main vehicle for the gel. You can test this or assess the gel using viscosity measurements, and that will give us behavior of the gel as we apply shear. And you can see that it will have the same kind of behavior where we have the pseudoplastic effect. That means when we apply shear, the gel start to thin, so we'll have a thinning effect. Another test we can do is to measure the amount of the drug released from the gel system. And the way you do this is using in vitro assessment using France diffusion cell. And that will allow us to measure the amount of the drug that diffuses through a membrane. So as you can see here in this animation, this is measured across on the left, the drug is diffusing across the membrane to the right part. So this is the gel matrix on the left, and it goes into the release medium, diffuses through the membrane. Hence, this is called France diffusion cell. And then you measure. If you look on the right, the time on the right on the x-axis is increased, and the drug is increased as the time progresses because the drug is moving across the membrane. There are tests that we can do to assess the quality of the final gel. The first one we do is the appearance of the gel. It should be clear with no lumps or bubbles. The pH must remain at between 5.5 and 7, and that should confirm to us that we have achieved correct neutralization. But also remember that is important to avoid any irritation to the skin. The viscosity is also very important because it needs to stay thick enough so it remains on the skin, and should be go thin when it is when it's rubbed. And this goes what we mentioned before about the pseudoplastic behavior. So it should be easy to apply and rub. Finally, the drug should be released and in a proper way, because this eventually will release the drug into the skin. And we use the France cell as shown earlier. There are some things we can expect, and then also as mentioned in other formulations, there could be interactions. So the carbomer, which is can increase the viscosity, it will lead to thicker gel, but then that can lead to slower drug release. On the other hand, you have the solvent, which is the industrial methylated solvent, which is basically alcohol rich. This is because it's a solvent, it can lead to thinner gel, but on the other hand can lead to better penetration, but because it's alcohol, it will dry faster. The interaction between both of those may the way we look at this is, if we increase the amount of the IMS or the solvent, then that means we need to increase the amount of the carbomer to keep it thick. If we increase the propylene glycol, the other part in the co-solvent system, then that will help to keep it moist for longer. So basically here we need to ensure a balanced system where we have balanced thickness, drug release, and skin feel. And then again, they do this using this contour plots or contour map to help achieve the best or the optimum.